you can reference this in your free time lah. Okay, wait, let me call my whiteboard. Okay, how are you doing on the other classes? So far, okay?
Actually, research methodology, I already finished the class.
Very good. That's not a difficult
Maths
class.
haven't started yet.
Yeah, Maths. Thanks for highlighting. I have to talk to Dr. Vijan. Sometimes you got teething problems. It's been a
He's the one
while since
teaching.
he talked. Dr. Vijan? Actually, you can write him an email also. I give you his email address. Sometimes you just push him a little bit, and then you get your friends also to send him email. Then if he gets email from a bunch of you, he'll be like, okay, I really need to get it done. Because he told me he would actually have started in the 3rd week already. So I thought he started. So I was surprised that you mentioned it lah. But don't take it resting lah. Try to just send him an email, that kind of thing lah. So I'm going to post you his email here. Okay, so you got his email already, right? You just share it with your other classmates lah. Privately lah. Ask, okay, we haven't started yet, so can we all just individually send him an email like in the next couple of days, so that this kind of like remind him a little bit lah. Okay, I myself will remind him, but sometimes if he hears from the students, he'll be a bit better about that lah. Okay. Okay. What we'll be doing, we're going to go to the whiteboard now. Okay, let's go share content. Let's go to the whiteboard. Okay, today I actually want to give you a preview on memory systems lah. Start talking about memory. Let's see why is this white thing not? Okay, because the philosophy of this class is actually I want to teach you digital design from the perspective of memory systems design for a few reasons lah. Currently, the trend of memory of digital systems design is you no longer will design the computational units lah, like the arithmetic units. In the old days, like 5, 10, 20, 50, 30 years ago, you spend a lot of your effort designing the arithmetic units, the logic units, the ALU. You spend a lot of time there because compute was the limitation. But because of the law of scaling that we have actually been doubling the transistor speed by Moore's law, only because we shrink the size of the transistor. Today, the bottleneck is not computation. We actually can compute things way faster than we can bring the data. So the bottleneck is communication. Okay, communication is the bottleneck. So actually, most of our computing is done on load store architecture. So I think you're familiar with computer architecture. There's a memory, and then you have an instruction, and the instruction is actually going to fetch some data from another location of memory, put it in the registers, then activate the ALU, and then send it back to memory. Okay. Everything is like fetch from memory, do some operation, return to memory. So that's a load store architecture. You load from memory, you store back into memory. Okay, and because of that, memory access and the communications lines lah, either your bus, your cross bus switch, or your point-to-point links, high-speed serial links, these are the communication bottleneck. Okay, so the design, the focus of IC designers and digital systems designers are now more towards how can I already take all these digital blocks, the ALUs, the multipliers, the adders, these are I've already got fantastic, highly optimized design, but how can I combine them onto different chips and add new functionality? That is their goal. So the focus is actually on interfacing communications between modules, okay, and resource allocation. That is like synchronization, arbitration. Let's say you got more than one request to use the same resource. How do you manage the request and all that? So that's why we're actually focusing more on these kind of aspects to demonstrate lah. Because the memory system, number one, is fast becoming the bottleneck lah, especially for cloud-based systems. Because you have a lot of data, and it's the locality lah, how close and how quickly can you fetch the data. That is the issue lah. And then the modern memory systems actually have a lot of high-tech engineering to actually make the data transfer fast. Not just latency, but most of the time is throughput. You're increasing the throughput of data to and from the memory system. So a lot of the high-speed logic, the glue logic, the interfacing logic, if you study memory systems, you will get among the best in digital systems design lah. So a case in point, your DDR4 now, the memory bus, what is the speed of that? That I think is like a range of gigabits per second, or thousand. It's already in the gigabits per second range, and your Ethernet is not even that fast. Okay, so that's really high speed link lah. Okay, so we start with the basic concept of memory. Normally I like to start by saying a memory is just a bunch of blocks lah, a bunch of boxes. Okay, it's a bunch of boxes. In each box you can store a bit. Okay, so here I actually have 16 boxes. Okay, 16 boxes here. Each of these boxes I can store 1 bit lah. Okay, I can store and I can retrieve 1 bit. Okay, so how do I access a box, right? So I actually have an address which is actually activating a particular box, and I actually have a bus where I can actually send data into that box, or I can retrieve data from that box. Okay, and I actually have a pin that says, am I reading or am I writing? Okay, read, write. Okay, right. I have address. Come on, so annoying. Hmm. Okay, address, and I have data. Okay, great. So my address pin, the first principle is, if I have an n-bit address, I have 2 to the power of n boxes. Agreed? Okay. And you look at this address, I've done it in a particular way where you can see there are certain number of rows this way. Okay, there's 4 rows, 1, 2, 3, 4, and there are 4 columns, correct?
Yeah.
Okay, so which means that in this particular memory configuration, I actually have 2 bits for row address and 2 bits for column address. Okay, I can easily also create a memory with 2, 3, 4, 5, 6, 7, 8. 3-bit column address, 1-bit row address, and vice versa. So you start to see there are a bunch of permutations I can create this, right? Yeah?
Yeah.
Okay, great. And I want you to keep that in mind, that for the same capacity of memory, there are different architectures for this memory, how you want to create them. Okay, right? Okay, now, what are these boxes actually? Okay, what are they? So if you're talking about SRAM, static RAM, 60 cell, each box is actually a transistor, a set of gates like this. Let me show it to you. Let me share it in a second. Let me share my screen. If you're talking about, okay, you see, right? This is a 60 cell. Basically, this is a NOT gate, this is a NOT gate, and with 2 pass gates. Okay, so this is a 60 cell, and this is what we call static RAM or SRAM. Okay, so I'm going to come back to my drawing board screen here. So in a digital circuit, basically for static RAM, each box is basically 6 gates in this kind of configuration. Not signed. Okay. So what happens is this regenerative, like if this is a logic 1 here, logic 1 will put logic 0
I
here.
cannot see the screen.
Oh, you cannot see the screen. Oh, okay, okay. Let me try again.
Mm.
Can you see the screen?
Yeah.
Okay, look at the lower right side of the screen. So what we're talking about now is you're saying that what is each of these box? How am I storing a bit? Okay, a bit for static RAM. So we're talking about static RAM or SRAM. Okay, you've heard of SRAM before, right? Okay, where is SRAM used? SRAM is used in your registers. So if you've done microprocessor programming, you actually have certain registers, right? You know, you use the registers to set the configuration for, you know, maybe the on-chip peripherals in microcontrollers, or you want to actually access to do ALU operation. So that's your registers. Static RAM can also be used in cache, level 1 cache, the cache that is the fastest, the smallest, and the closest to the processor. Level 2, level 3 cache, sometimes they don't use static RAM, they use dynamic RAM. Okay, we'll talk about dynamic later, but in a static RAM, each of these 1-bit cell is represented by this, we call this a 60 cell, 6 transistor cell, 2 for each NOT gate. And basically what this NOT gate is doing is, I have a logic 0 here, it becomes a logic 1 here, logic 1 here becomes a logic 0 here. So the positive feedback is regenerating and remembering that value. Okay, so if I want to read, I just basically open this gate and make sure I can read the value. If I want to write, I make sure I open this gate, I think in one of these, and then I write, and then I just force a different value to this regenerative amplifier. That's how it works. Okay, this is the 60 static RAM cell. But there's also another technology we call dynamic RAM, DRAM. And this is even more interesting and primitive because this one is cheap. And why is it cheap? Is because every single cell is literally a capacitor. That's it. Okay. And if you're thinking about what a capacitor could look like, well, it could be as simple as a MOSFET here. Yeah. Okay. Maybe you don't even need to do the doping. And then this is your bulk terminal. You connect your bulk terminal to ground. The gate bulk terminal, that's your capacitor. It could be as simple as that. So every bit in a dynamic RAM is literally a capacitor, a capacitance. Okay. And now you start to get worried, like you say, if it's a capacitor, it's like, how the heck does it store value? And you're right. This capacitor is on the order of femtofarads. Okay, so that's pretty small, right? So if you can calculate the voltage across here, again, modern voltage is 1.1 volt or 1.8 volts. Q equals CV, you can calculate you get capacitance. If you take 1 femtofarad, you can calculate the total amount of charge. And so you're like, wow, this charge can leak. And you are absolutely right. DRAM is very compact and it's very cheap because every bit is just one capacitor, whereas a static RAM is expensive because every bit is literally like 6 transistors. Okay, and DRAM is power efficient because to retain 1 bit, you only need to spend the amount of charge here. Static RAM is expensive because you are kind of like doing this regenerative thing and you have to drive the bits and all that. Okay, so the problem with DRAM is it loses a charge quite easily. And therefore, what you need to do is periodically, you need to read out this capacitance and recharge the capacitance. And this is known as refresh. So whenever you come across refresh in a DRAM circuit, you know why, because the DRAM, every bit is literally just a capacitor, and the capacitor is leaky, and if you don't refresh it, it will just disappear. The value will just disappear. You lose the value. So this is why they said DRAM, when the power goes off, it goes away. But it's even more sinister in that. Static RAM, the power goes away as well because you lose the ability to regenerate, to drive. So lose the bit. DRAM is even worse. Even if the power is not turned on, if you do not refresh this, you lose the value. So first principle is everywhere you use DRAM, you need to refresh. And refresh is nothing else but you read the value here and you charge. If it's a logic 1, you need to add refresh the charge until it goes back to full. If it's logic 0, it's logic 0 lah. It's okay. You don't have to do any charging lah. Okay.
Okay.
But you have to do this refresh period and you have to do it pretty frequently lah. Now I forgot off the top of my head, but in one of the assignments I've actually given you the refresh rate lah. I think it's something like you have to do a refresh once every millisecond or something like that lah. There's a fixed standard, certain number of refresh. Okay. Right, so the way that DRAM is organized is basically there's a whole row, okay, and there's a bunch of what we call bit lines, lah, okay, and these bit lines, there is a capacitance connected to it, lah, another capacitance connected to it, lah. Okay, maybe let me draw it a little bit better lah. Okay, let me draw it something like that. Let's draw a pass gate. Okay, then another pass gate. So this is a 3-bit row, but we won't make 3-bit rows. We typically make the row as a multiple of power of 2 lah. Okay, but I just wanted to show you this idea because this is a bit line, this is a bit line, this is a bit line. So each of these line, okay, let me draw in red lah. Okay, this is a red line, this is a red line, and this is a red line. Oh gosh. This is a red line here like that. Okay, and this red line basically is the connection of this whole column, the connection of this whole column, the connection of this whole column. Okay, and connected to this red line is basically a gate, a transistor, and then connected to the transistor is actually the bit lah. Okay, and all these transistors are connected here. And then there's another row of transistors, okay, that are also connected to the bit line like this. Okay, and now we'll go shortly into why I have to draw this for you, because this goes to the way that memory is accessed. Specifically, DRAM, how is accessed. Okay, like that. And then third one, you actually have like that. So you've got all these rows of boxes. Okay, each capacitor, you've got row, first row, second row, third row. You got as many rows lah. It depends lah. It's how many row bits. That's how many rows you have. And all these transistors, the total number of rows, all these transistors are connected to the bit line, right? And each of these transistor here is a switch. If you enable this bit line, if you send a logic 1 here, all these capacitors will actually charge up this line. So these lines will take the value of this capacitor. Okay, so that's how a DRAM is read. You would select an individual row, and all the boxes in the row will actually go to all the bit lines. And at the end of these bit lines, there's actually a, if you can think about it, there's a bit of a D flip-flop lah. At the end of this big line, there's just a bunch of registers at the end of that, so that when you charge, when you turn on a particular row, all the capacitors will load their value onto this bit line, and then that bit line will actually store a logic and remember that. Okay, so it will remember the whole row. That means the way I read it out, the first step is I select a row, and the whole row is then sent to a buffer, a row buffer. Okay, and then this row buffer will go through a multiplexer circuit, okay, and the column address will select which output to send out to the data. Okay, this is the way memory is read. Dynamic RAM is read. Okay, there is a row access that is to select one particular row, because that will load all the bits into that row, into the bit line, and then it will be stored in the row buffer. And then there's a column access, which is just basically accessing a multiplexer to send out the value. Okay? And if you notice, if I do my row access I destroy my bits lah. Okay, because all the bits are going to be, the charge is actually just going to go and charge up this line, right? So I destroy the bits here. So dynamic RAM is also bad because every time you read it, it's destructive. So after you read, you have to recharge the whole thing, pre-charge it. Okay. Okay. So now you realize that this dynamic RAM, the cheapness comes at the cost. You have to do a pre-charge operation before and after you read. Okay. So the thing is that because these lines are so long, the capacitance is very high. You know, we're not going to go into the circuit design, but I'm just letting you know like these lines are actually pre-charged. And what happens is some of the charge is actually lost to the capacitance or some, there's a small change in the charge here, like the total charge here, but it is actually pre-charged first so that you don't actually totally empty out because this capacitance, the amount of charge here is not possible to charge up the whole line. So you need to charge up all these lines first, and then there's going to be a slight delta charge on this, which then these amplifiers are going to amplify here. So it's not exactly a D flip-flop. It's actually called a sense amplifier, where there's a small differential signal change there, and that differential signal change there will be amplified into full logic 1 or full logic 0. Okay, this is how they keep memories at low power. But the key point here is to tell you the origin of the actions that you need to perform. That is, when you want to access a particular bit, you need to do a pre-charge, which is setting up all these memory bits, okay, to getting ready to read. Then you need to do a row access called a RAS, okay, and then RAS lah. Then all the bits will change this charge and then will be amplified at the sense amplifier. The sense amplifier is just basically a row buffer lah. And then there's a column access, which is just basically multiplexing, choosing through a multiplexer which of these bits you are going, and then after this whole process, there is a restoration, a charging restoration of the charges here. And above all that, right, because this is only affecting the row that you're reading, but there are going to be some rows that maybe you never read. And those rows will need to be refreshed periodically within a few times within 1 second. 1 second, you have to refresh them a few times. Okay? You understand that? Okay, yes. Good. Now, I've shown you how an array of DRAM looks like, okay, and I show you that you can actually have your total address bit is n, so the different configurations of architecture you can actually have different split. So you will take out of the n bits, you allocate certain portion to the row address, certain portion to the column address, and now you understand why there's a difference lah, because the row address means that if this 8 here, you mean you read 8 bits in one go, and that will be buffered in the sense amplifier. And if it's 4 here, then you will buffer 4 and then you're just playing off between the number of rows and columns and that will actually play off in different ways, because again, if you've got fewer rows, there are going to be fewer capacitance attached to this line, so the capacitance on this line will be less, so it's going to be faster, less able to charge. But then the downside is the row access will take longer because you've got way more transistors that you have to activate and all that So there's circuit trade-offs here that relate to the speed of access, which you're not going to be covering in this class. If there was a VLSI class, we will probably cover it, but VLSI class, we also probably won't cover it because this is very standard design. I think you can look it up in the book. But I'm just telling you that this is, the configurations will lead to, different configurations will lead to slightly different access times and all that. And that's why your memory has so many versions, right? You have version with, 4 and all these kind of things. But I just want to let you know it's there. But this is only one bit. Okay, so how do you get a 8-bit memory? Your memories don't come in 1 bit, right? They come in 8 bits or 16-bit or 32-bit or 64-bit, right? So how do you get an 8-bit? What you do is you take a bunch of these arrays, okay, and you connect them to the same row and column access, right? Okay, you take a bunch of these. So if I want an 8-bit output, so in memory is actually, they put it times 8 If they put times 8 means the output of that chip is 8-bit. Okay, so you've seen in DDR, sometimes you have a times 4, sometimes you have times 8, sometimes you have times 16. Times 8 means it's 8 bits output. And that just means that there are 8 arrays, okay, which all share the same row and the same column. So now you can actually see where the 2 to 4 decoder is, because if I've got 2 to the power of n rows, okay, so I need a n to 2 to the power of n decoder. So my address will be in terms of n bits, right? So if I've got 2 bits, I need to convert that to decoder lah that is enabling any one of these 4 rows. Okay, so that's where it goes. Okay, that's a decoder circuit here. Okay, so that decoder circuit, there will be a decoder circuit for this. If I'm doing an 8 width, I'm going to take 8 arrays, but they can all share the same decoder circuit. They can all share the same row decoder circuit. They can all share the same column decoder circuit, right? Because they're addressing the same row and the same column, correct?
Correct.
So what I call this is row, this is column, and this is bank. Sorry, this row column and this one it's not called bank lah. This is the bit lah. So this whole 3-dimensional thing is called one memory bank. Okay, so when you hear about one memory bank, it is basically you have a row and column decoder that they all share, and then there is the actual memory array lah, which is the array of capacitors. And then there's a certain number of them that's replicated lah, to get times 8 bits, or times 4 bits, and that is one DRAM bank. Okay. All right. This is terminology lah. Okay. Can
8 bits means it's just one row only.
It's not one row. Again, it's not one row. I didn't say anything about the rows here. Okay, row and column here. I can have, if it's this one 8 bits is the data 8 bits. Okay, so let's distinguish. There is the address bits and the data bits in memory. Okay, memory, there are 2 types of bits. There's the address bits and you have the data bits. Okay, so what you're actually used to in modern processor systems, the address bit and data bit is the same lah. Okay, if you think about it lah, you tend to assume that the same, but they're not exactly the same lah. So like say a 32-bit machine, your data bits are all 32. Okay, but you assume that a 32-bit machine can get 32-bit address, but if you count to the power of 32, it's way, I think it's about 4 gigabytes lah, if I'm not mistaken. That's why in 32-bit system you cannot exceed 4 gigabytes of memory. Let me do the math here very quickly. To the power of 32 divided by 1024 divided by 1024. Yeah, that's right. So 32-bit system, you actually have 4 gigabytes of memory. Okay, because you have you have like 4 billion locations. To the power of 32 is about 4 billion. So you can only have up to 4 gigabytes of memory. That's why any computer system that is more than 4 gigabytes has to be a 64-bit system. But 64-bit systems today is way more than 16. 64-bit is to the power of 64. It's very large lah. It's basically 1024, 1024, 1024. You actually can get 17 billion gigabits. Okay, but obviously our 64-bit systems, we don't have that much memory, right? You are thinking at about 8 to 16 gigabytes is enough for now lah. Okay, so that's why I'm trying to tell you that just because your memory has that much address space doesn't mean you use all of that lah. So in most practical systems today, like laptop systems with 8 or 16 gigabytes of memory, you have something like 34 to 36 bits of memory address bits, but you have 64 data bits. Okay, can or not?
Yeah, can.
So out of the 34 or 36 address bits, you can allocate lah. You can see, okay, I want how many rows I can have. Maybe 16 bit for the row, and then 18 bits for the columns, right? So usually what will happen is the memory will tell you is 248. The row has 248 columns. Then you automatically will know based on the size how many rows it has, right? Yeah. And the catch here is that you cannot grow memories arbitrarily large. Okay, up to a certain point, people don't milk memories that large. I think what I've seen is I think the limit is about 256 megabytes. And beyond that, what they do is they actually tile. They actually group together blocks of 256 megabytes. They will never build a memory larger than 256 megabytes. You will not see a 4 gigabyte array. Why? Because as you can see, the more capacitors you add here, the more storage you add here, the greater the capacitance on the line, the slower the circuit, the more energy it requires. Okay, so getting large memories, the way they do it is they group together banks of a certain size, and usually is about 256 megabytes or 512 megabytes like the most. But I think I've seen about 256 megabytes usually lah. Okay, I don't think they've gone beyond that. Okay, and that gives you an interesting perspective. Why? Because it's going back to what you've seen in the earlier part of your combinational logic, right? You know, you have a bunch of smaller circuits like the 2 to 4 decoder, and then they ask you to build a 4 to 16 decoder. So memory is already using that same technique. So you can now see that there is a motif in digital design where you design a smaller bit part and then you can put them together a bigger part. I give you three different motifs really. One is the decoder, as you've seen. The second one is the comparator, you've seen. Carry adders also, you probably have studied them, or you can actually look up. There are plenty of examples. You get a 4-bit full adder, and then they ask you to make a 16-bit full adder out of the 4-bit full adders. And by you use the carry logic, right? And here you see the same idea. I'm going to build a 4 gigabyte memory array, right? Out of a bunch of 256 megabyte arrays, something like that. Okay.
Mm.
And this idea of building up from these basic circuits is very interesting because you get to operate them in parallel. Very interesting, huh? Parallelism. This is one of the big advantages, right? Because, for instance, I can have, if I'm using 256 megabytes, okay, and I'm trying to cover maybe a 2 gigabyte space. So that means I will have 8 arrays of 256 megabytes. And they cover different portions of the memory address, right? If I've got 2 gigabytes, I probably have 31 bits of memory address. If I've got 256 megabytes, I divide that into 4. So 31, maybe there are 29 divided into 4. Divided into 4 will be 31. Roughly about 8 bits each lah. Roughly about 8 bits of memory address each. Is that 8 bits? No, that's not quite. No, that's not quite true. It's about roughly about 31, 30, 29, about 29, 28 bits each lah. Okay, 28 bits of address space each. And I have, so 8 of them will be 27 lah, 27 bits of address each. And then they will cover 2 to the power of 27 different memory regimes lah. So if I have one memory access that belongs to the first 256 megabyte array, and I have a second memory address going to the second 256 megabyte array, I can actually serve the two requests simultaneously. You got that?
Yeah.
So this is another strong reason why we want to break things up. And same idea with the 2 to 4 to 4 to 8, right? Decoder. Okay. If, for example, you're having a decoder that it's doing, you probably don't see that lah, but maybe in an adder you can actually sort of see, I can add the first 2 bits first, then I only add the second 2 bits, and then it's like maybe I don't need all the parts at the same time. And then this idea of pipelining where I can actually add the first 2 bits first, and then before the next 2 bits arrive, I can actually do some other work there, right? So if I add the first 2 bits first, then I wait for the next 2 bits to come, and the next 2 bits come, I add the next 2 bits. But I already added the first 2 bits, so the first 2 bits I can use to add for another stage, right? So this idea of actually breaking things out into chunks allows me to parallelize it, allows me to pipeline it. Okay, so this is why it's really, really powerful, and this is the core design motif, design idea that is allowing us to increase throughput, not latency, throughput. Okay.
Okay.
You got it? Okay, good. So now 8 bits, you know that I just have 8 parallel arrays, and they are all addressed by the same row and column logic. We can share the same one. This is called a bank. So a bank will be basically a group of address spaces and gives you 4 bits or 8 bits lah. But then again, you don't have 8-bit data sizes now. You have 32 bits, right?
Yeah.
Or 64 bits. So the way it's done is actually you collect 8 banks, so that will give you 64 bits, or 4 banks, that will give you 34 bits, and they will cover different part of the data. Okay, all right. And typically why it's called a bank is because each bank typically is one chip. One chip is a bank. Okay. So if you go and open up your computer, you look at the DDR RAM, you see that the DDR RAM actually has both-sided. They're like 8 or 16 chips on both sides. Everything of this black colored chips is on both sides. So within one chip, there's actually a few banks, okay? And each of these individual chips, okay, they are tiled on one side. One side is called a channel. Okay, so you actually have two channels on, so it's a dual channel, one side and the other back side, right? Okay, and then they actually have, they're serving different parts of the memory. Then within each channel, there are a bunch of ranks, okay? I think a rank, if I'm not mistaken, is a group of chips lah. Okay, so I will connect a bunch of banks together to get my 32-bit or 64-bit, and all the banks that form a 32-bit or 64-bit is called a rank. Okay, and I can have different ranks that will address different parts of the data. Okay, and that could be my channels, right? So there's specific terminology at this. I'm not being very accurate here, but the general idea that I've been able to find is banks is more of like they share the same row and column decoder. They are the same 1-bit array. They just tile times 8 times 4. That is a bank. Okay, and sometimes one chip has one bank. Sometimes one chip has 4 banks. 2 banks. Okay, and because they're banks, they will cover different part of the memory. Okay, so if I have a 4-bank chip, it means I can have 4 parallel accesses to different parts of the memory. If the accesses are on the same part of memory, then too bad lah, I have to wait. If they're different part of memory, I can actually increase the throughput by 4 times. Okay.
Okay.
All right. And if I actually have a rank, I actually combine a bunch of banks, and they're actually not on the same chip. I combine a bunch of banks on different chips to form a rank, and that rank gives me my full data width. Okay, that's the pattern that I can see. And then you also have channel and all that, like you have even further level, but you can start to see how they are combining parallelism in different ways to allow you to access different memory location simultaneously, different part of the memory simultaneously, so parallelism, and also to allow you to access different, to actually build up the bit width from 32-bit or 64-bit, but still retaining the speed of like a 8-bit or 4-bit back. Okay. Right. Okay. And this is what makes DRAM access complicated lah. So as you can now imagine why we're talking about this, is a perfect digital system actually to study parallelism, pipelining, and also how do you do resource allocation, because the banks and the ranks and the channels will be sharing a data line and an address line. And the address and data line, the processor doesn't care about banks and ranks. The processor just says, this is the address, this is the data, or this address, data, lie. Right, correct? So the address is one common address and data line that goes to this chip. And then there has to be on-chip resources that decide this address and data line, who gets to use it, when do they get to use it. So now you can see that modern dynamic RAM systems actually have pretty complicated controllers whose main job is actually to figure out who gets to use what. And then better still, these controllers actually act as a FIFO buffer, or they actually collect a queue of instructions from the processor, and then they dispense this instruction to the individual banks and ranks to address that particular data. So there is actually a processor on your DRAM system lah. There is, okay? That's how it's done. So that's why you can do out of order execution and all that. Like everything, the core controller is basically, you can think about it as a processor, but it's not exactly a conventional processor. And there's pipelining and all this and all that. And if you want a little more detail, it's all in the Jacob's book. Okay, and we'll take selective chapters, okay, depending on how fast you can go. All right. Okay, if you understand that bit, now I'm going to talk about this idea of synchronous DRAM. Okay, so far I've been talking to you about DRAM. Nowhere have I mentioned a clock. There's no clock here. We're just talking about the organization, parallelization, which possibly can lead to pipelining. But then when you talk about pipeline, you need a clock, because the whole idea of pipeline is that I'm actually doing an operation, complex operation. That complex operation can be broken down into a series of tasks, and each of these series of tasks will use a different circuit resource. And because it is a series of tasks, means I do the task one after another, and each task one after another is using a different resource. After I use the first resource and I pass it on to the second resource, the first resource is no longer used. So using the clock as my synchronization mechanism, I can assign the first resource a new task. So pipelining is actually a form of parallelism. Okay.
Okay.
And the key idea behind pipelining is you have to split up your tasks into a sequence of subtasks, and each of these subtasks must use a distinct and unique resource on the chip. If you use the same resource, you cannot pipeline it lah. What's the point, right? Because the pipeline is the idea is that after it's done with this resource, something else can use, but the whole task is not done, but it's done for this particular resource and you can start using it for the next task, right? That's the idea of pipelining, okay? All right. So synchronous DRAM is this idea that, okay, you know, the row and column address, you know, it kind of takes time, lah, right? So if actually I do this row access, it takes time because I have to pre-charge all these bit lines, and it takes a while for all these capacitors to actually switch these bit lines for how many capacitors in that row there are, and then it takes a while for the sense amplifiers to actually ramp up, amplify the value to logic 1, logic 0, then you stabilize. So row accesses are expensive. But the sense amplifier is like a buffer. Once you access that row, you're fine. So once you've actually accessed that row, if you read any value within that row, the column access, it's just a question of switching the multiplexer, and that's very fast. Okay, so it seems like your memory access is actually asymmetric, meaning to say that if you want to access data within the same row, it's very fast after you've paid the price of one row access. But if you're doing random accesses across different rows, you'll be very slow, much slower than if you're doing random accesses on the same row. Okay, so it's in the interest of your DRAM unit that you can try to bunch together as much as possible all the column accesses within the same row before you activate another row. Okay, got it? And then this makes things a little bit difficult because if you are all this kind of different timing lah, you are accessing the first row lah, then you're accessing the second row, then you have to keep track of the timing. The processor has no time to keep track of all this because the processor is very busy. If it's not doing your job, it's got other job. It's a very high value thing. So you want to hide this from the processor. You don't want the processor to worry about this. So what do you do? People have come up with a very clever way to do this. They actually allow these memory accesses to be done in a synchronous form. Okay, so they allow everything to be done on the clock, and basically what they do is they have a mechanism where they allow you to read out a bunch of adjacent column values in sequence lah. This is why your modern processors, they reach a cache line. They never read one single cache value, they read the entire line, right? This is why lah, because they're actually fetching the whole line, the whole row, right? You already open the row myself, you fetch everything. Okay, that's why caches are always updated by row and not by value or not by single elements. Okay, so it's the same thing here lah. So what happens is there is some additional controller logic that will actually pay the row access price, and then it will read up the columns one by one, and the column values will be output on the edge of the clock lah. Okay, so it looks like your data access is actually the clock cycle, because you're coming out every clock cycle, the strobe lah, the every clock cycle you're coming out one column address, then the next column, then the third column, then the fourth column, all in the same row. Okay, so synchronous DRAM is actually some additional controller logic where you don't actually have to switch the address lines one by one. You actually put in a base address, and the controller will actually give you a certain number of contiguous row locations within that row lah. Okay, whether it's 8 or 4 or 16 or 32, and sometimes in some controllers you can actually change the number lah of contiguous accesses that you make lah, and it will actually update these values automatically on clock cycles lah. Okay, there's some advantages to this, because if you are a processor and you're changing the address line, and you're a processor, you are very far away. You are far away from the DRAM compared to the internal DRAM controller. So your lines have more capacitance, and so if you are trying to change the address from, if you're trying to make a row read, right, read across the row, you are going to spend more energy and take more time to actually flip the bits of the address line. So it's actually more time saving and energy saving for you to just say, I give you a base address and you already have been configured to just give me 8 contiguous values from this base address or 16 contiguous values from this base address. So I just give you this base address and I expect to read all of these out every clock cycle. Okay, so as DRAM controllers do that, they give you a batch of numbers where the processor only needs to give you a base address and then you get this back. Okay, and so there's some internal controller logic which involves a counter and all that, and I've implemented a basic form of this in Verilog as a reference for you. Okay, but I've done it for the read and I've asked you to do it for the write. Okay, so that's the first realistic design that I'm asking you to work on. Okay, let's go to it and then see. So I'll share with you some of the assignments that have been put up. Okay, and then I'll go ahead and create more assignments on the FPGA, more material on the FPGA. Okay, so the first thing that you have to learn about SDRAM basically is this idea, how do I actually go for a synchronous DRAM. The synchronous DRAM okay, is actually here SDRAM design with bit slice. I will enable this. This you can read the textbook Jacob chapter 7 and 8. This is actually implementing the synchronous DRAM. So what I do is in practical module 3, I give you some code, some basic code. I've only implemented the read part, but I'm asking you to complete the write part of the circuit with the Verilog design as well as the test bench. And in practical module 2, I actually have a behavioral model of the SDRAM array. Okay, I'm actually planning to update the behavioral model, but I don't know if I can get around to it this semester where, you know, if you actually don't obey the timing by right, I should give you a don't care and all this kind of crazy thing. But right now it's not doing that It's just a very simple behavioral model. Here in this assignment, the goal is actually for you to think very carefully about how you want to implement a high-level state machine controller, right? Because I've already walked you through this idea that you have to do a pre-charge and a calibration task for your DRAM. So there has to be a state machine that takes charge of that. So here I'm actually showing you, for example, the DRAM configuration is a 64 megabit DRAM times 4. So that means the bank actually has 4 this one, and then I give 4 bits. Okay, that means there are 4 banks in four arrays, DRAM arrays, single bit DRAM arrays that make up one bank, and then 8192 rows, and then there are 4 banks. So you should have plenty of information here. How is this organized? And then I'm just giving you a bunch of the basic command. This is basically the command from the processor to the SDRAM controller. This is the time it takes for a row access, a time it takes for a column access, and this is the time it takes for the multiplexer to place it from the multiplexer to the data bus. And this is the burst, the burst mode, which is I'm saying you're actually sending a sequence of values from the row, and this is also the write time. Okay, and I'm actually showing you. I'm saying that these are the basic elementary operations on the DRAM array or the SDRAM array, but the processor doesn't control this. The processor just gives you a higher level command, which is a read command, and the read command is basically I'm saying there's two command T command times. Okay, then there's a TRES, row access, a column access, a burst, and then the pre-charge. The pre-charge is actually the bit lines are being brought high again so that they can be ready for the next goal. So I'm giving you that this particular controller actually has random read, random write, contiguous read, contiguous write, and refresh, random refresh, and refresh only the open row. Okay, because open row means the RAS has been selected. Okay, and I'm actually just giving you kind of like the number of approximate clock cycles it takes, and then I'm telling you that the refresh must execute one row every 7.8 microsecond because the DRAM standard actually specifies that you have to refresh 8192 rows for every 64 millisecond. That this is a standard for SDRAM. Okay, you can look this up. So basically, I'm just giving you that this this 7 states, right? Because this 7 state corresponds to the high level commands you receive from the processor. So it's up to you to design a state machine, which is basically the top level state machine for your SDRAM controller, that if you actually receive an read command, you know, can you actually have a sub-state machine where you are doing the waiting for the T command to execute, and the T rust, and the T cast, and the T burst, and the refresh lah. Okay, so I'm asking you to design that circuit in Verilog. Then you complete the implementation for rust and cast signals, right? Like based on this controller, you are actually generating the rust and the cast signals. Okay, and then you build the test bench, and it's possible you draw the circuit lah, and then you modify the control, the SDRAM controller to actually have a T bus, a variable T bus lah, 1, 4, and 8 lah. Okay, all right. So this is that first assignment on the SDRAM controller. Wait, let me go back to this one. And the second assignment basically is you've got the complete SDRAM controller along with the SDRAM itself lah. Because SDRAM is actually a DRAM plus a controller to enable burst mode and clocking. So in this first part, I've already given you that example, and in the second part you have that. And then I just want you to group up all of these to form one bank of ×4 lah. Like you can just use the same configuration from the top. Okay, so you can get that done quickly. That will be good lah. And then I've given you some video from another university, which I think it's one of the IITs is a pretty detailed exposition on memory. It's got a bit more details than what I walked through you just now, but I walked you through the gist already. And you have this as well as the Jacobs textbook, given the relevant chapters. Okay, Bruce Jacobs textbook, you can read that, and then you can start to, then you study the design. The design is half complete, and then you repair it, and you optimize it, you simulate it, draw block diagrams, and then you submit it. Okay, that is your real world assignment. So you can get started on that ASAP lah. Okay, right. So that is kind of the basic thing that we'll be doing lah. But if you have more time, then we can go on to the core, which is very difficult, the more difficult parts, which of these kind of 3 other remaining modules lah. Okay, I'll explain to you a little bit more about these modules. There's the load store architecture. Basically, okay, let me see where I can find my. Here. Okay, just give me a second. I'm going to call up a circuit file, a circuit diagram, just to show you. Okay, can you see it?
Yeah.
Okay, this is kind of like my top level diagram of what the whole thing should be like. Yeah, it's this one that you're actually going to building up, you know, banks of DRAM here, and then I actually want you to have kind of like 2 channels lah. Okay, this is an earlier design, but I think the later design is something like this lah, where this is actually the load store part. Your processor is actually going to send instructions here lah, but the instructions basically, are you doing a contiguous read, are you doing a random read, and then what is the address, what is the data, and all that. There's a certain instruction format lah, okay, associated with this. It's going to put into a FIFO. So this is a queue, and then your FIFO, there's a controller from your SDRAM. So everything within here is your SDRAM controller. So your SDRAM controller is going to fetch the instruction from the FIFO. It's going to figure out, is it in the address space for this first bank, or this first channel, or the second bank? Is it in this first bank or second bank? If it's the first bank, you will allocate the scheduler, so the address and data will go to the first bank. If not, you go to scheduler will send it to the second lah. And if you do this right, while you are actually processing the instruction from 154, you can actually select the instruction that goes to the next bank. Your scheduler will switch to allow this even without the instruction being completed here. And basically, I've done this code, I've assembled it in assignments 456. I've done it up only for the read part. I've not done it for the write. So you have to handle all the multiplexing for the data output and ensure that the data is there and all that. So this is the complete big picture, but we are going to split it into a further few parts. The first part I told you was the high level controller. That is, if you have a command, how is it going to work? Your processor going to spend how much time. The second part is actually, I told you, the bit slicing. You have some code that is just this two-dimensional. The DRAM is just 1 bit. You actually have to extend it to 4 or 8 bits. So you have to make it into this bank like that. The third part of the code is actually the FIFO to actually handle inputting instructions and fetching and decoding the instructions. Okay, the next one would actually be pipelining. That is, I going to try and look at this DRAM access, split it up into a pipeline. But I've done not really a great job. I've just broken up to a 2-stage pipeline because didn't have time the last time to actually go through all the examples in the Jacob book. But the Jacob book actually has examples on how they actually break it up into a multi-stage pipeline. So if you really can go reach that stage very quickly, then you will basically be studying how to write that pipeline from scratch to pipeline these read and write accesses. You look at the Jacob's book to study all the possible combinations for that. And the final one will actually be to actually design this crossbar switch along with the scheduler. And I have a very simple scheduler. It's just kind of like first priority, just like the priority encoder that you have. But you can actually do really complex scheduler, right? That is out of order scheduler. Like you're looking at the address here, then you're just fetching the first out of order one, and then you're executing, right? Because again, you may actually have two or three consecutive access to the same bank, and then the fourth one is actually to a different bank. So why are you going to wait for the first two? Why don't you look ahead, pick the fourth one and send it out? And there are techniques from out of order processors, super scalar processors that you can apply to do this. For example, you can apply Tomasulo's algorithm. So like I said, these projects all can grow very big and you can go very complicated. And if you are at this level, Douglas, almost guarantee you Intel will take you. I'm serious. If you can show me a working design with the test bench and all that, I will put you in touch with Intel and with Opstar. They will interview you and they will take you. I'm pretty confident of that, if they have the headcount. Okay, because I've mentioned to you I've at the undergraduate level, students have done project with me. The most recent one, he did a serializer deserializer. He did the Verilog design as well as the channel simulation and model using MATLAB. Straight away, the Opstar engineering director listened to his final year project, interviewed him after that, and he haven't even graduated. He's graduating in September. I think he just got finished everything, but he got a job already with Opstar. So we have connection with Opstar, with Intel. Intel specifically, I have a good connection with the high-speed links group, the links doing the group doing the PCI, USB and all that. We know some of the principal architects and all that. So it's not too difficult to actually recommend you to get a job there. But because we have some history with them, I've got a few students really there. At least 2 students that they've been kind of interested in, so they know that if there's a recommendation, they will take it quite seriously. So as long as Intel has an opening, it should be no problem to recommend you. But you need to do your part, right?
Yeah.
You need to really show your talent. So here, the reason I've designed it in such a way is because when you go to the Intel interview, you can just whip this out to them based on this design, and they'll just ask you a question on this design. This counts as your technical interview already, right? Because it's not that easy, this one. But it's not that difficult either, because this one is actually a watered down version. We've not even done the memory error correction and all that. There's a bunch of other circuits that needs to go into this that we've not considered as all, totally at all. Okay, but this is a fair goal, a fair sample. And where I intend to insert the FPGA is right now, if you are using the simulation tool, which is the EDA playground. I hope you can get to the point where you are taking my Docker using this Qflow and you're using Icarus Verilog and Yosys for simulation. Okay, because you should actually simulate post-synthesis. That means do the synthesis and simulate on the synthesized design, not on the behavioral design alone. The behavioral design is called behavioral simulation. Behavioral simulation just tells you whether your logic is right or not. More or less, did you get it sort of right? But it's a very high level. After behavioral simulation, you need to do synthesis, and after simulation synthesis, you have to do post-synthesis simulation. So my hope, if you want to touch on the FPGA, is you do post-synthesis simulation, because the post-synthesis simulation is going to target your design. It's going to convert it into gates, discrete logic gates, and we are actually able to, using these tools, to actually select our technology library, meaning you'll be able to see exactly like this is a 45 nanometer, 45 micron technology library, or 45 nanometer technology library. Which gates were used? You can look at the timing parameters of the gates, and the timing parameters of the gates will be inserted and taken into account into the Verilog in simulation, right? So pre-synthesis, if you're doing right now what you're doing with just the assignment one, you're just doing on simulation on the behavioral. In no way, you've not taken into account any of the propagation delays. Okay, so your circuit is ideal, everything's ideal, it's switched on the spot. But as later on after you finish your sequential circuit assignment, I will cover timing and metastability with you, where we actually look at setup time, hold time, the concepts behind this, and then you actually have to check your margins, and then you have to take into account clock skew and all that, so that your circuit, the combination logic, will settle less than the clock cycle, and then you will actually understand how the setup and hold time and the combination logic actually sets the frequency of your design, the maximum frequency of your design. So that's where your real, it separates the man from the boys. The really great IC designers, really, they can handle all of these, and their logic is like super, and can actually meet all the timing and all that. But I just wanted to walk you through the process of that. But the reason I want you to do post-synthesis is because it's realistic with the real delays from the process technology, and we will be looking at the possibility of getting you to synthesize the design for FPGA as well as for ASIC. So the ASIC library is already there, the 45 nanometer or 240 nanometer micron, 25 micron from Auckland State University. We can use a bunch of different gates, but if you want to do FPGA, I can do 1 or 2 sessions where I just prepare some video lectures. I describe to you the FPGA architecture and the specific points where you need to understand, because the design process is the same, okay? But where it's important is to understand the FPGA architecture and how do you actually map it. The implementation is different. In ASIC, you actually have the standard cell library, which is a bunch of standard gates okay, that is defined and all that. In FPGA, you have your equivalent standard cell library, but they are your configurable logic blocks if you use Xilinx terminology okay. And basically most of the combinational logic is implemented as lookup tables. Basically, they are small blocks of RAM and then there are some flip-flops that you can enable coming out of that RAM. Okay, that's why I emphasized the last lecture. I actually emphasized combination logic and flip-flop is actually the basis for all sequential state machines, because now you can clearly see this, how is it working in an FPGA, because the FPGA, instead of implementing discrete gates, they implement lookup tables, which is nothing else but a ROM or RAM doing the combinational logic being driven to certain flip-flops, and the flip-flops has different configurations. You can actually configure them as a register chain, or you can enable them, disable them. And then you also have a bunch of crossbar switches, which is what you're going to design in the bottom part here, this module 6. Crossbar switches will actually decide how you connect one combination logic with flip-flop to another combination logic flip-flop. That's the basic high-level architecture of an FPGA, but we go into a bit more detail. Okay, sounds good? Excited? Yeah. If you're excited, it's good. I just because this course is, to be quite frank, so far it's been pretty challenging to Malaysians so I also feeling a little bit like waiting for a star student to come and prove to me that you can actually extract the maximum worth out of this course lah. Because I'm finding myself in a hard place. Like after going through like 1 or 2 rounds of students, I'm feeling that okay, I probably need to simplify this course. Cannot teach all these things, but you know, as I shared with you, that there's so much that you can really master from this course. It's just how fast can you go only, right? So if you are motivated, you know, just complete as much as you can, as quick as you can. I give you feedback. We go on a rapid feedback, and then as you go on, I can make the problems more and more complex lah. But I think lah, if you actually manage to complete up to module 6, and then some FPGA, on this basis alone, Intel will be quite keen to listen to you lah. Yeah, yeah. Okay.
Okay.
All right. So what I'll do is I'll just enable all of this. So you just do it at your pace lah. And then we will kind of meet every week, sort of. Sometimes we meet 1 hour, sometimes meet 2 hours. Let's just depend lah. Let's see on your progress. I think what I'm anticipating, hopefully, is you can quickly update, change, and resubmit the combinational logic one. And by next week, before Thursday lah, I hope you can submit for the sequential circuit one. So I can give you comments. You can really make sure you master the fundamental, because we cannot go on beyond these two. The last offering of this, that was my mistake lah. I went to the students. I straight away gave all these modules, and then they didn't even get this thing done, and I didn't realize their combination and sequential was so bad. So they couldn't actually follow lah. So this round, I'm like, no, you guys have to show me you can do these two first, then we'll move on. Okay. Okay. Then the algorithmic state machine, you just look through it lah. This is chapter 5, chapter 6 of the True textbook. If you find it useful, you use it. I haven't actually found it that useful lah, because I can do all the things in the sequential state machines, the milli and mole machines. I can do everything in that, so I don't actually need the ASM tool. But if you find that it's useful, it helps you, go ahead and use it. Because it's not my role here. I don't really think the most value you can get out of this is learning all these tools. It's actually learning all these methods of design and doing real designs. That's the value of this course. And then where you do a design, then you miss out this, you miss out that. Then I tell you, okay, you have not implemented this one, you have not covered this test condition, all these kind of things lah. Okay, that's where I see the value is, and you are learning SDRAM system lah. So the reason we're not going for DDR RAM is because I think SDRAM is plenty complicated already lah. And then I checked with Intel guys, they said actually if you can design SDRAM, so it's enough for them lah. Because DDR RAM you need more time. The main difference on DDR RAM is the accesses happen on both clock edge, positive and negative clock edge. That's the main difference. Everything else is kind of the same lah. SDRAM, the synchronous only on one clock edge. DDR RAM, you have to make sure that you can actually do the read and writes on the positive edge and the negative edge, right? So it's double the rate lah. So you actually have to do more crazy stuff with the parallelization to get that kind of throughput lah. Okay.
Okay.
Okay. All right. I'm sort of basically done for tonight. Unless you have questions, what I'll do is I'll go ahead and unlock all of these. You just let me know. You just keep in touch with me when you are reached a certain level, and if there's anything that seems inconsistent to you, you just WhatsApp me lah. So I just can give you that personal attention. My work here will be I'll try to prepare some additional material on FPGA to give you that kind of introduction here. And I think there was something that was missing here that I wanted. Maybe I will give you access to the VLSI video where I actually describe the front end and back end process because in the past these two courses used to be offered together, but this semester I was actually offering DSD especially for you because your IC design batch didn't have enough courses so I have a video prepared where I actually talk about the VLSI systems design flow So it's this one here you can see. I'll give you the link to it. There, right, right, yeah. So explain to you how things work the big picture of it. So I'll share with you these two videos, the links, and you can just listen to that for some background knowledge lah, because it introduces the Q flow, the tools, and all that as well lah. Okay. Okay, let me do that plus FPGA material, and I think that should be enough for this semester. All right.
Okay.
Okay, so yeah, resubmit your assignment, then I think I'll grade it very quickly. But I'm more interested in your sequential one for next week. Then let's plan on having the class again 9 to 11 next Thursday. And then from there, it's just how fast can you move on the rest of the assignments, okay?
Okay.
Okay, and then I'll try to add some FPGA material and I'll give you some introductory videos. Great. Okay, Douglas, any other questions?
Currently no, but if I got, I will WhatsApp you.
Okay, sure, fine. You're still working full time, right?
Yeah, I'm working full time.